What's up, guys? It's your teacher, Mr. Weiss, here with another amazing video about Newton's second law, and this time we're going to explore it for angled forces. So let's go ahead and dive into this problem. So this problem says, in college, Mr. Shadell used to pay the bills by working in the shipping and receiving unit of a printing plant. This often meant pushing around heavy pallets of paper products by applying a downward angled force with an angle of 38 degrees. One day he had to move a particularly heavy pallet with a mass of 844 kilograms from one end of the room to another at a constant velocity. Earlier, he determined the force of friction to be 100.9 newtons. What is Mr. Shadell's applied force in the x direction? So over here, we can see that he's pushing down on this pallet, creating an angle, just like we said, with the horizontal. So we'll see that applying this angle force downward, and here's our horizontal, that this angle right here is the same. So let's bring that out over here so we can really see what's happening. Here's our downward applied force, and this would be this force applied. Here's our angle. We know that the angle is 38 degrees. And then this is going to be the x component of our applied force, or in other words, Fax. And then this one is going to be our y component, or Phi. Question is asking us to figure out what the x component is of that applied force. Piece of cake. We actually don't even need this triangle right now to figure that out. And the reason being is that there's a little hint or clue inside this problem. And the clue is that it says that we're moving at a constant velocity. Constant velocity is going to tell us that net force in the x direction is just 0. And it's 0 because acceleration is 0. Therefore, because we know that net force is 0, that just means that the forces that point to the right are going to be equal to the forces that point to the left. So let's go ahead and draw our free body diagram really quickly over here. We see that we have force gravity pointed down. We have this applied force pointed down as well. And then we have force friction pointed back in the opposite direction of motion. And then lastly, we're going to have force normal pointed up. We know that force normal is going to be bigger than usual because we have that downward force pushing down on our object. Therefore, our net force in the x direction is just going to be the forces that point to the right, while force applied does point to the right, and it points to the right in the x component. So it would be force applied x minus force friction because that points to the left. And we know that this is 0 because we're moving at a constant velocity. Therefore, find out that force applied x is just equal to force friction. And we know what force friction is. It's given to us in our problem right here, 100.9. So force applied x is just 100.9 newtons. All right, let's go ahead and look at number 2. So number 2 says, what is Shadell's force applied in the y direction? So this one is a little difficult because it's kind of a different way to solve for this that we haven't done before. But if we take our triangle and we just bring it down here really quick, we're going to notice that this angle is 38 degrees, just like we had above. And now we have force applied x. That's 100.9. We don't know force applied y. Fortunately, though, we can see that this force applied in the x direction, the 100.9, is really just our adjacent side. And the force applied y is our opposite side. Therefore, we can go ahead and use tangent to solve for the force applied in the y direction. We know that tangent of theta is just equal to opposite over adjacent. If we plug in those two values, we're going to find out that tangent of 38 degrees is equal to the opposite, which we don't know, force applied y, that's what we're solving for, divided by 100.9, because that's force applied x, or the adjacent side. Multiply the 100.9 over, and we get force applied in the y direction is equal to 100.9 times tangent 38. Do the math real quick, and we find out that force applied in the y direction should just be equal to 78.13 newtons. All right, 2 down, 2 more to go. This one says, what is the weight of the pallets? Well, weight is just referring to force gravity, and force gravity just means mass times gravity. So in the problem, it told us mass, and it said the mass was 844 kilograms. Gravity is just 9.8 because we're on Earth. Multiply those two together, and we find out that force gravity of this pallet is 8,271.2 newtons. All right, last question, number 4. What is the normal force? Well, to figure out the normal force, we're going to have to use our net force and the y equation. We know that force normal points up. We can see that in our free body diagram right here. We also can see that force gravity is pointing down. So we're going to subtract force gravity, and then we're going to notice that force applied in the y direction also points down. That can be seen over here in our triangle. So minus force applied in the y direction. All of this is equal to mass times acceleration in the y direction, but it's not accelerating in the y direction, so that's just 0. So now we're going to manipulate this equation to solve for force normal. So let's add force gravity over the other side, and let's also add force applied in the y direction. Now we just go ahead and plug our numbers in. We know these numbers because we just solved for them. Force gravity is 8,271.2, and force applied y is 78.13. Do some simple addition, and we find out that force normal should be 8,349.33 newtons. Okay, let's take a look at number 2. So number 2 says Mr. Weiss is water skiing off the back of a speedboat. Huge flex right there. The rope pulls with a force of 38 newtons at an angle of 39 degrees from the horizontal. Mr. Weiss skis with a constant velocity of 18 meters per second and has a mass of 86 kilograms. Key words here, constant velocity. What is Mr. Weiss's net force in the x direction? Well, net force in the x direction is just equal to the forces that point to the right minus the forces that point to the left, but also mass times acceleration. If we have a constant velocity, we aren't accelerating. Therefore, our net force in the x direction is just 0. Well, what about the y direction? Same thing. In the y direction, net force is equal to the forces that point up minus the forces that point down, or mass times acceleration in the y direction. Constant velocity again, it doesn't say that we're accelerating in the y, so we can assume that we are not. Therefore, net force in the y direction is also 0 newtons. So number 3 says, what is the force of tension in the string in the x direction? So let's go ahead and draw this force that's being applied and showing the angle. So it says a 38 Newton force, so here's 38 newtons, is applied at an angle of 39 degrees from the horizontal. That's right here. This is our force of tension in the x direction because it's the horizontal part, and then our force tension in the y direction is the one that points up. In order to solve for force tension in the x direction, we notice that this is the adjacent side, so we're going to need cosine. So cosine of 39 degrees is equal to adjacent force tension in the x over hypotenuse, 38 newtons. Multiply 38 over, and we get 38 times cosine of 39 is equal to force tension x. Plug this into our calculator and solve, and we find out that force tension in the x direction should just be equal to 29.53 newtons. Alrighty, number 4. So number 4 says, what is the force of tension in the string in the y direction? So there's 2 ways we can solve for this. We can do the trig again, or we could just do a squared plus b squared equals c squared. But let's just keep rolling and use our trig. We notice that FTY is the opposite side. So that means that sine of 39 degrees is going to be equal to the opposite force tension y over the hypotenuse, which is 38. Multiply 38 over, just like we did before. We get 38 times sine of 39 is equal to force tension y. Plug it into our calculator, just like we did, and we find out that force tension y is 23.91 newtons. Again, we also just could have used our a squared plus b squared equals c squared, and said that force tension x was a, force tension y was b, and our 38 newtons was c. Plug those in accordingly, and we also would have got our answer. Number 5, what is Mr. Weiss's weight? Well, we know how to figure this out. Weight is just mass times gravity. And I said in the problem, my mass was 86 kilograms. Gravity is 9.8 because I'm just on Earth, and Earth has a gravity of 9.8. So multiply those two together, and we find out that force gravity of Mr. Weiss is 842.8 newtons. Number 6, what is the upward force on Mr. Weiss from the water? Talking about force normal, kind of, but in this case, we'll just say force normal. So we're going to have to use our net force in the y equation, and we're going to have to take our forces that point up. We know force normal points up, but we need to figure out what other forces point up. So really quickly, free body diagram, we see that force gravity points down. We see that this applied force is pulled upward. And then we see that we're going to have force normal also pulling up. Since our applied force is pointed upward, that means that the y component of our applied force is also going to be pointed upward, which means that we're going to have force normal plus our force applied in the y direction. And then gravity points down, so we're going to subtract gravity. We know the net force is equal to 0. Now we can go ahead and add force gravity over to the other side. We get force normal is equal to force gravity, and then subtract force applied to the other side, minus force applied in the y direction. We know what these two values are, so we're just going to plug them in. 842.8 for gravity, and force applied y is 23.91. Now we just add them together and we solve. We find out that force normal should be 818.89 newtons. All right, last question. What is the force of friction between the water and the skis? So let's go ahead and use our net force in the x direction now. And if we see here, I left it off my free body diagram for the previous problem because it wasn't important for that, but I'm going to add the force friction right now. And I see that force friction points this way, and force applied in the x is going to point in the opposite direction. Therefore, I'm going to have force applied x in the positive direction minus force friction because it points in the opposite direction. Those are going to be equal to 0 because the net force is 0. Therefore, force applied x is really just equal to force friction. We already solved for force applied x, so that means that force friction is just equal to 29.53 newtons. And again, the reason why we knew all this is because of these two simple words up here, constant velocity.